We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
In February 1930, 24-year-old Clyde Tombaugh was scanning photographic plates at the Lowell Observatory in Arizona. He found a tiny speck, Pluto, the ninth planet. Since its discovery, our only close-up views of Pluto and its giant moon Charon have been artists' impressions. Late 2005, after 17 years of planning, NASA's New Horizons spacecraft was being readied for a critical 4-week launch window that opened on January the 17th, 2006.
And liftoff of the Atlas V rocket with
This mission will be the fastest spacecraft ever launched from Earth. Its destination? Pluto. Cape Canaveral, the home of NASA's Kennedy Space Center.
3, 2.
It's the launch pad for many interplanetary voyages. On Pad 41, a powerful rocket was being prepared to launch America's fastest spacecraft. New Horizons will be conducting its science mission further out into the solar system than any other craft.
This is where the all rubber meets the road down here at the Kennedy Space Center.
Kennedy's payload hazardous servicing facility, a giant intensive care unit for spacecraft and rockets. Huge clamshell fairings will protect New Horizons as it speeds through Earth's atmosphere. More than 20 meters tall, they're carefully hand-cranked into position. Preparations are nearly complete.
We've been working hard for the last few years just to get here, but there's still a lot of work left to be done.
In the Kennedy clean room, the New Horizons spacecraft took its first short flight. It's about 2 meters from the tip of its antenna to its base, about the size of a grand piano. But it only weighs about 450 kilos.
The main difficulty about going to Pluto is that it's so far away. The Earth is almost 100 million miles away from the Sun. Pluto is 30 times that far, 3 billion miles away. To get to Pluto in our lifetimes means it has to go very fast. Its average speed is more than 10 miles per second. And to do that, it had to be light.
One of the unique things about New Horizons is that we built a very light spacecraft and bought a very large launch vehicle. And the combination is ferocious. It gives us a very high flyout speed because we have a very long way to go.
New Horizons' planned launch speed will take it past the moon in 9 hours. The Apollo missions took 3.5 days. A slingshot gravity assist from Jupiter will provide a speed boost, cutting travel time to Pluto by 3 years.
And then we just continue speeding, but we have a very long way to go. 5 billion kilometers across this great depths of the outer solar system to reach Pluto. And that's what takes the time. So it's not that we're dawdling, we have a long way to go.
Why send a spacecraft on such a long and difficult journey into such a challenging environment? For the science team, it's a voyage back in time to see close-up evidence of how solar systems form from clouds of gas and dust.
We're going to learn about how planets are built, because what Pluto is a planetary embryo, an object that's partially formed as a large planet, a stage in planetary formation that the Earth went through, that Mars went through, that all the larger planets had to pass through this size scale, but here we see an object that didn't get any further.
And if you think about the solar system, we have the 9 planets. 4 of them are the so-called terrestrial planets. They're rocky objects in the inner solar system. Mercury, Venus, Earth, and Mars have a lot of similarities. Then you step out a little bit further and you get into what are called the gas giant planets. These are huge objects which are dominated by large amounts of molecular hydrogen and helium gas. And that's Jupiter, Saturn, Uranus, and Neptune.
And that was it. We sort of stopped there. And then there was the little misfit Pluto at the outer edge of the solar system. Poor little Pluto, all on its own.
Then in the 1990s, came a series of discoveries that changed everything.
Feature that we found in the outer solar system is called the Kuiper Belt. It's this group of things that call them asteroids. They're similar sized bodies to things that we've been calling asteroids all along. They're different in the sense that they're these icy bodies.
And once we discovered the Kuiper Belt, everything sort of fell into place. The understanding that, in fact, Pluto and Charon are members of this other class of objects called the ice dwarfs.
And in fact, we think that these ice dwarfs are the most populous class of planetary body in our entire solar system.
That tells us, from that respect, Pluto's not special. It's got lots of company out there.
Ice dwarfs aren't just far out there. 4 billion years ago, they may have had a role in shaping Earth and bringing to our planet the materials of which we're made.
The collisions within the Kuiper Belt produce the short-period comets, which then fall in towards the sun and bombard the Earth, sometimes bringing some of that raw material from which life formed and some of the water that's on the surface of the Earth.
This information about the Earth's birth isn't available anywhere else.
So the key part of that big puzzle of how the solar system formed will come from looking at Pluto, understanding its nature and everything about it.
Understanding Pluto means understanding how the Earth was formed. With the New Horizons launch a few months away, the clean rooms at the Johns Hopkins Applied Physics Lab and NASA's Goddard Space Flight Center were buzzing with activity. Lead scientist Alan Stern had been advocating a mission to Pluto for about 17 years.
The key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on.
All right, everybody, thumbs up. Yeah! Thumbs up.
Dr. Stern led the team of 50 planetary scientists who designed the New Horizons instruments.
It's a mission that takes a few years to build and a decade to fly, and then we'll have the data analysis. It's something that'll change the textbooks for the remainder of the 21st century, if not longer. So it's a life's work, and it's whatever it takes to get this built.
This first trip to Pluto will survey the basics. What do Pluto and Charon look like? What are they made of? What's their atmosphere like? The hunch is that all these questions are connected.
With Pluto, if you want to understand the atmosphere, you have to understand the surface. If you want to understand the surface composition, you have to understand the geology. If you want to understand the geology, you've got to understand the atmosphere. It's all tied together, and so we have instruments to study every aspect of Pluto.
The 7 science instruments on board New Horizons are small and light, with low power consumption.
This big barrel is a telescope called LORRI, the Long Range Reconnaissance Imager. It's our biggest, most powerful camera in terms of resolution power.
The cameras are key. For over 60 years, Pluto remained little more than a blurred dot. Even the Hubble Space Telescope couldn't show any detail. This true color image is the best that could be produced with Hubble. Pluto clearly has a varied surface, but whether these are mountains, or craters, or polar caps remains a mystery. At this resolution, there's no more information. Here's what Earth would look like at the same resolution. All the richness of the surface and atmosphere would be missing. That's where New Horizons wide-angle camera will come in.
Football field-sized resolution at Pluto, we're going to be able to, to see things thousands of times more precisely than what we've been able to do with the Hubble Space Telescope.
The science team wants to know not only what Pluto looks like, but also what it's made of. That's the job of another part of the wide-angle camera, the LISA infrared detector. Science team member Will Grundy demonstrates LISA's principles.
In my backpack is a Field Spec Pro, which is a field portable spectrometer. It's very similar in capabilities to the LISA instrument on board the New Horizons spacecraft in that it's able to see out to 2.5 microns. Infrared spectroscopy is one of the most powerful techniques that we can use to tell about the compositions of remote surfaces. Sunlight comes in, illuminates the surface, bounces off into the spectrometer, and some wavelengths don't make it back. Some wavelengths do, depending on the chemical composition. On Earth, we only really have one kind of precipitation. We have water, and sometimes it comes down as rain and sometimes it comes down as snow.
On Pluto, it's thought that exotic ices like methane, nitrogen, carbon monoxide condense out of the atmosphere as solids, never as liquids. That's not surprising. Pluto's temperature is believed to be minus 228 Celsius, just 45 degrees above absolute zero.
To the human eye, lots of different ices look pretty similar. They all look white, pretty much. We have here carbon dioxide ice, and snow, of course, and also paraffin wax, which is an organic compound which is pretty similar to the methane ice on Pluto. And they look all white to the eye, but to the infrared spectrometer, take a look at how different they look. Methane ice, carbon dioxide, and water ice. And all three of these substances look pretty similar to the human eye. They all look white, but in the near infrared, they're very different from each other because they have different molecular structures and they have different vibrational modes, and so they absorb different wavelengths of infrared light.
Pluto's surface seems to have about the same brightness as freshly fallen snow on Earth. And it sometimes seems to behave more like a comet than a planet. When its eccentric orbit brings it closer to the Sun, its surface heats up, producing a denser atmosphere. An instrument called ALICE will use a different part of the electromagnetic spectrum to study the atmosphere.
This is the ALICE ultraviolet spectrometer, which will probe the composition of Pluto's atmosphere and also study its surface.
It measures light with a shorter wavelength than what you and I see. We fly past Pluto, that's the antenna direction. We're going to turn, so the antenna is pointed back at Pluto, back toward the Sun. And we're going to watch as the Sun passes behind Pluto, and we're going to see the sunlight get absorbed at these ultraviolet wavelengths, and we can tell what the atmosphere is made out of at these different heights.
Studying starlight as a planet eclipses is the same technique that was used to discover Pluto's atmosphere. If a world with an atmosphere passes in front of a star, the light will dim gradually, rather than suddenly blinking out. Scientists call this occultation. In 1998, a team flew an experiment aboard NASA's Airborne Observatory. This guaranteed clear skies above Earth's clouds and the ability to follow the path of the Pluto eclipse over the ocean. The orbit that brings Pluto closer to and further from the Sun is thought to create seasons, with weather that resurfaces the planet with fresh, bright ices. Some researchers think this is what creates the light and dark regions. The plan is for New Horizons to get to Pluto before winter sets in, and the atmosphere freezes back down to the surface as solid ice. REX, which stands for Radio Experiment, will track how signals to and from Earth vary as they pass close to Pluto. Two more instruments will study how the solar wind, the constant stream of subatomic particles and energy flowing out from the Sun, interacts with Pluto. SWAP, the name means solar wind at Pluto, and Pepsi will be able to sense Pluto from great distances.
We can smell, if you will, Pluto from 1 million kilometers away with Pepsi. And we can detect the extent of its atmosphere by feel with SWAP, possibly from as far as 100,000 kilometers away, but certainly as we get into tens of thousands of kilometers.
Last of the 7 instruments is the student dust counter. Every part, from logo to detectors, was designed entirely by students at the University of Colorado.
Its job is to profile the density of dust particles all the way across the solar system for the first time. But the real breakthrough of this instrument, it's the first time that students have been able to build a flight quality instrument on their own and fly it on a mission to a planet.
So what's the big deal about dust? We have dust everywhere. Dust in your house, dust outside, dust all out the solar system. Well, dust comes from the grinding up of material that gets shed and left around. In the case of the solar system, we believe that the dust that's flying around the solar system was produced by the grinding up of asteroids, the grinding up of Kuiper Belt objects, the grinding up of ring particles and so on, that is left over from the process of not just forming the solar system, but its constant evolution over time.
The students also face review boards of veteran scientists and engineers. The SDC wouldn't fly if it didn't serve the science objectives and have every chance of working. Unlike missions that go into orbit around their target planet, New Horizons will be traveling so fast there's no way to slow down. After a 10-year trip, closest approach to Pluto and Charon will flash by in less than a day. So the mission operations team needs to practice. In reality, it's June 2005. But at the Applied Physics Lab, it's already Encounter Day in July 2015.
The ability to practice things in those years far out there are all part of the planning now to assure mission success then.
The operations team is working on a highly realistic mission simulation of that critical 24-hour encounter period. Pluto is so far away that radio signals from Earth take 9 hours to get there and back. Every aspect of the encounter, from navigation to operation of the science instruments, must be programmed in advance.
That was like 7 minutes ago.
There are many years of planning that go into each of these events that we'll execute when the spacecraft is in flight. And that's what this test is all about, is practicing that whole process and the software that's involved.
And this is going to be incredibly nerve-wracking. As we do the encounter, we get one shot at flying by Pluto. That's both terrifying, also very exhilarating.
5740 and 5720.
If an instrument fails to turn on as planned,
5802.
if a thruster burn starts a fraction of a second late, then the spacecraft will have lost its only opportunity to study Pluto up close.
Someone may say, well, why are you doing an encounter test that doesn't happen for years? Why are you doing that on the ground? And the response is that we do not like to do any kind of flight software loads in flight because it's risky. So what we want to do is find out all the problems that we might have with that software on the ground. And the way to do that is to try to run through all the various activities that we're going to do in flight on the ground.
Then what is different? This is what I think is different.
Running the simulation in real time is meant to reveal problems with communications and with the computers that are the mission's lifeline to the distant spacecraft.
So far it's going pretty good. Just some minor things we weren't expecting.
You can't anticipate all of the problems, and some things that you never anticipated happening will happen during a mission simulation test. And of course this makes us better operators of the spacecraft because we've seen those problems, taken care of them.
We're about 10 minutes away, almost 11,000 kilometers, which is what we've set up closest approach to be.
Closest approach, and the computer triggers the infrared spectrometer.
So what does it look like?
Right now we're scanning about the...
So this is the LISA scan at 124 microradians?
Yes, so you're scanning at negative 124 about the body.
One purpose of the simulation is to translate all the computerized data into three-dimensional reality.
Pluto here, and I've got us flying by this way, and I've got the Z into the page.
Okay.
So minus Z is up. Oh, I know what we need.
The rehearsal does its job.
The pointing summary.
They detect a potential problem. The cameras aren't pointing where they should be to capture key data.
And we missed Pluto, but it's only a sim, so no worries.
So the sim was successful. It identified a bug that can be fixed. More mission simulations, plus the Jupiter flyby in 2007, will give the team more opportunities to refine their procedures.
We also have to be sure that we have in-depth documentation so that we can understand what we did in 2004 in 2015.
Many of the faces around New Horizons are relatively young. That also is no accident.
You have to have a longevity plan. And normally we're focused on instruments in the spacecraft surviving that duration, and we don't get to Pluto till 2015. And for people, we have to have a longevity plan.
Before they were ready to ship the spacecraft to Cape Canaveral, the hardware also had to go through a rigorous test program. And keeping on schedule was critical.
If you want to fly to Pluto on the quickest route, you need Jupiter in position. And that means we have to launch in January of 2006.
It's also important that we get there as soon as possible because Pluto does have an atmosphere right now, but it's moving farther and farther away from the sun. And at some point, that atmosphere is going to freeze out.
What we have left on New Horizons before we launch is to integrate the spacecraft and test it.
When one builds a spacecraft, you build the individual boxes and instruments first, and they go through their own tests, both functionally and then environmental tests. And that's sort of equivalent to the members of an orchestra, each tuning up. But once you build it as a spacecraft, once you've assembled it, then you're playing the symphony. And that's what we've been doing. We've been testing it as a system.
And then we test it again, and then we test it about 5 more times.
And if we have surprises along the way as we're doing the work, we want to have time in our pocket to make up for those surprises. So we actually want to get the work done ahead of time.
Our current list of tasks is in the tens of thousands.
It feels a little bit like being strapped to a train going 500 miles an hour.
Once we launch this, we can't go after it with a screwdriver. We can't go fix anything that isn't working.
We make sure that we carry plenty of spare equipment on board the spacecraft. If our main computer breaks, we have a backup. If our main transmitter breaks, we have a backup.
And the test program, the full-up test program, is more than a year long. A big part of the testing that gives us confidence that it's going to work in flight is the environmental testing. So we put it into an environment that's pretty much exactly like it's going to see on its way to Pluto and at Pluto. That includes a thermal vacuum tank where we put it in this big tank, we pump all the air out, it's in a vacuum just in space, then we heat it up and we cool it down just as it's going to see when it's actually in flight. Another very tough thing for the spacecraft to endure is the launch itself. On these rockets, they're gigantic. They shake a lot. If you've ever seen a paint shaker at a hardware store where it mixes the colors into the paint, that's exactly what the spacecraft is going to go through during launch.
And feels, in fact, at burnout of the third stage, I believe 13 Gs, so 13 times its own weight is what it's feeling. And that structure has to support all of that.
One of the things we do is we put the whole spacecraft on a gigantic vibration table, a paint shaker, and shake it. And then test it after that, and shake it again and test it again. So that's what we're doing from now until launch.
Once fully tested, the spacecraft took the relatively short trip to Cape Canaveral. The New Horizons spacecraft had to be moved to Cape Canaveral to be united with the rocket that would blast it on its way. A January 2006 launch would put Jupiter in position to give the spacecraft a slingshot boost toward Pluto.
This is pretty definitely high on the stress level curve. Getting the spacecraft moved from Columbia, Maryland, all the way down to the Cape is pretty tough.
Like packing for a long trip, everything needed must come along. Test equipment, spares, tools.
Everything we're doing is the last time we do it. We want to make sure every bolt is exactly tightened, fastened correctly, everything's been assembled, tested, the records are kept properly because there's no going back. This is a flight build.
Everything arrived safely in Florida, and the final preparations began. But they almost didn't get this far. In 2000, plans for the Pluto mission were in jeopardy due to budget pressures. A 17-year-old student, Ted Nichols, helped keep the dream alive.
You know, I just wanted to see us go there and see what we could learn about it.
With the Pluto mission in danger, he launched a website petition from his bedroom. Interest from press and public was enormous.
It actually crashed my website at one point. I think I had so many signatures in the one file that it actually reset. So Reuters, the Associated Press, and all kinds of other press agencies. And then the next day, an article came out that the LA Times did about the efforts to save the Pluto mission and why it was so important to go there. At that time, we put together all the petition responses and printed them out and bound them in a book. And all the petitions, not including the ones that were lost, came in a bound book about that many signatures.
Thousands of signatures went to the president and Congress.
It's a group of people that really made a difference in this website. You know, I allowed people to express their interest.
NASA reconsidered. A Pluto mission was on again.
Really exciting to me is, you know, knowing that one day I'm going to sit down with one of my kids and be going through a textbook and there'll be all this information on Pluto on there and they'll finally be pictured. And I'll also be able to tell them the story of, you know, how I started this little website petition that put together a lot of support and, you know, helped to get this mission off the ground.
One of Ted's teachers told him not to bother. Nothing he could do would make a difference. But Ted did make a difference. And 75 years after the discovery of Pluto, a close encounter is becoming a reality. The story of Pluto begins in Arizona, at the Lowell Observatory, named after its founder, Percival Lowell. He was captivated by the possibility of water and life on Mars, and then by the search for Planet X, an undiscovered world beyond Neptune. Pluto was discovered here, and the observatory remains a center of Pluto research today. Astronomer Mark Buey personifies the ingenuity and persistence it takes to study Pluto.
Part of why I like Pluto so much, because it's a cold, icy place.
Dr. Buey's role in New Horizons is to identify targets far out in the Kuiper Belt, where the spacecraft will travel after it has flown by Pluto. This instrument, named Mimir, after a Norse god of wisdom, will be placed on ground-based telescopes to study ices on Pluto's surface before the spacecraft gets there. Mark Buey hopes this information will help prepare for that all-important close approach.
The better an idea we get about predicting what we're going to see, the better we can tune the experiment and what we do when we get there. We've got one shot, we've got to fly by, we've got to decide, okay, we're going to do this, but you can't say, oh, gee, that's what it looks like, let's try this. You know, it's all going to be what we can guess ahead of time.
For 2 decades, Dr. Buey and his colleagues have been mapping the planet. In the mid-90s, he and Alan Stern used the Hubble Space Telescope to make the first direct images of Pluto's surface. In 2002, astronauts placed the new advanced camera for surveys on board Hubble, supplying data for a new map. Dr. Buey created a makeshift supercomputer that has been humming away for months at the Lowell Observatory. The data finally produced this map of Pluto.
I think this map is probably the best map we're going to get prior to the spacecraft getting there.
Pluto clearly has dramatically varied geology, though the images remain unclear. Yet 75 years on, the transformation from the dot of light that was Clyde Tombaug's first view of Pluto is remarkable. His equipment is kept at the observatory, as its director, Robert Millis, is proud to demonstrate.
75 years ago, Clyde Tombaugh sat at this machine and became the first person to ever see the planet Pluto.
The machine is called a blink comparator. He used it to look at photographs of the same patch of sky, taken a few days apart. Night after night, he'd patiently exposed the large glass plates. Day after day, he'd blink the plates back and forth, looking for anything different from the fixed points of starlight. Decades later, Tombaugh could still recall how uncomfortable and challenging the search for Planet X had been.
You get cold, you get numb. It took a lot of perseverance, because this gets brutally monotonous.
Blinking back and forward, he was looking for anything that shifted position.
The only means you have identifying a planet is going to be small. It's like a small star image. The only clue you have is it shifts position with an interval of a few days in the night's time. That's the only clue you have. So you've got to see all these star images, hundreds of thousands of them, to see if any of them shift position during the interval between the first and second plate.
That small movement was just what he saw on February the 17th, 1930. The arrows show its position a few days apart. Tombaugh had achieved his goal, the discovery of a distant planet. An English schoolgirl, 11-year-old Venetia Burney, came up with the name Pluto, god of the underworld. PL were also Percival Lowell's initials. By studying the motion of that dim and distant dot of light, astronomers discovered that it takes 248 years for Pluto to orbit the Sun. The angle of its orbit is steeper than other planets. Its distance from the Sun also varies more than any other planet. For 48 years, that was our sum total of knowledge about Pluto. Then, in 1978, astronomers Jim Christie and Bob Harrington analyzed new photographic plates taken at the US Naval Observatory. Dr. Christie noted an elongation of the planet. 1 month later, the bump had disappeared. Blink the images back and forward, just like Tombaugh had done, and the bump moves. Their conclusion? Pluto has a moon. Dr. Christie suggested the name Charon, after the ferryman of Pluto's underworld in Greek mythology, but preferred to pronounce it Charon, more like his wife's name, Charlene. From the motions of Pluto and Charon, astronomers worked out that the moon was almost half the size of its planet. So large that both objects spin around a central point, their mutual center of gravity. Pluto and Charon is the first binary planet discovered in our solar system. Using the physics of their orbits and their distance from each other, astronomers were able to calculate their mass and size. Pluto is about 2,500 kilometers in diameter, smaller than our moon, with about 1/10 of its mass. Together, they would barely stretch across the continental United States. From its size and orbit, astronomers estimated that Pluto is half rock and half ice. That makes it one of the largest of a new class of objects, the ice dwarfs, in what's known as the Kuiper Belt. This region is named after Gerhard Kuiper, a leading mid-20th century astronomer. He suggested that the solar system didn't end with Neptune and Pluto, but that there should be a disk or belt of other worlds far beyond them. In 1992, from an observatory in Hawaii, David Jewett and Jane Liu found the first Kuiper Belt object. They used highly sensitive CCDs, like the sensors in digital cameras. But their technique was essentially an updated version of Clyde Tombaugh's. They took carefully registered images of a patch of sky to see if anything moves against the distant stars. This one, QB1, did just that. They had found the first Kuiper Belt object. It was just a few hundred kilometers across. In 2002, Caltech astronomer Mike Brown and colleagues found a Kuiper Belt object half the size of Pluto. And in 2004, Sedna, another world, 3/4 the size of Pluto. Dr. Brown keeps looking, using computers to do the work of the blink comparator.
We do exactly the same thing. Clyde Tombaugh is the one who basically figured out the system for finding these things, but we do it all by computer instead. These are 3 images in a row that are blinking on the screen, just like Clyde Tombaugh would blink. On the morning of January 5th, 2005, I was looking at these very images, and I clicked the button saying this one's no good, and I suddenly see this object here very clearly moving across the frame in dead center. This is the one where I almost literally fell out of my chair, because it's perhaps, it's close to being the brightest object we'd ever seen out there, and it's also moving extremely slowly. Slow means it's far away. Slow and bright means it's really big. If you combined more distant with anything we'd ever found and almost the brightest thing we'd ever found, you knew immediately that this thing had to be the biggest thing we'd ever found in the outer solar system.
2003 UB313, the random name assigned by Dr. Brown's computer, was 25% larger than Pluto. Until an official name was chosen, he came up with a temporary nickname, commemorating Percival Lowell's search for Planet X.
We had actually been reserving the name Xena for the first object that we found larger than Pluto. We wanted something that started with an X for Planet X. We wanted something that was mythological. Now Xena is only TV mythology, not real mythology, but we figured Pluto is named after a cartoon dog, so that's okay. And we wanted something that, we decided there weren't enough female planets, so we were going to name another one female planet. So if you take those 3 together, you get Xena.
To Dr. Brown, the new discoveries far out in the Kuiper Belt make the New Horizons mission more exciting.
Pluto is the closest member of this new class of objects we're finding. The next best thing to studying all of these objects out there is to go look at some of the big ones. Go look at Pluto. It's not the biggest one out there, but it's the closest really big one that we can learn a lot about. So I think that going to Pluto is much more exciting today than it was even a year ago.
So, after 75 years of long-distance Pluto studies, the action shifted to Cape Canaveral. New Horizons may be light and relatively small, but launching it to Pluto required giant components.
We know we've got that starting line out there, so there's a lot of pressure throughout the whole flow to make sure we're doing all the right things to be ready for it.
All through 2005, hardware arrived at Cape Canaveral. The Lockheed Martin Atlas V booster, the third stage rocket, built by Boeing, flown in by the world's largest cargo plane, the giant fairings. The spacecraft itself was weighed to make sure no added mass will eat up fuel and reduce performance.
I'll let him give me the final weight.
We have to be polished and ready on the very first day of that window to go in order to get the best science, the best trip, maintain the highest fuel margins. We have to be ready to go on day 1.
Finally, it was time to lock the spacecraft inside the fairings that would protect it during launch. And a finishing touch, announcing New Horizons to the world. In December 2005, the spacecraft and third stage in its closed-up fairing, like a giant fragile egg, were placed on a huge transporter. With 9 axles and 81 wheels, it's able to raise and lower itself, to roll over bumps without tilting the cargo. They arrived at Pad 41 before dawn. "75 years after the discovery of Pluto. 17 years after a mission was first proposed. The dream of exploring the 9th planet was now only weeks from launch.
For most people on the project, in a sense, this is the end because it will be built and launched and on its way. But for the science team and the operations team, This is the beginning. This is where we begin the journey. Like a ship, we launch it.
The final push towards launch coincided with a burst of scientific discoveries.
The news is breaking almost by the month. We're really revolutionizing our view of the outer solar system.
At one point, we thought there was only Pluto out there. Now, every other month, it seems like we're discovering new worlds out there.
In 2005, Hal Weaver and Alan Stern used the Hubble for another close-up look at Pluto and Charon.
We want to know everything that could possibly be along our path as we're going through the Pluto-Charon system.
The result was an historic and astonishing discovery.
This was just incredible. In fact, it was so incredible we almost didn't believe it at first.
They saw two small dim moons, where only Charon had been observed before. It would double the excitement of the close encounter.
We get 4 for the price of 2. You know, instead of having just Pluto and Charon, we now have another couple of exciting moons to investigate. Pluto is an even more interesting place than we imagined.
Mark Buey confirmed the discovery by reanalyzing previous images. He made this portrait of Pluto and its growing family of moons. The distances between them aren't accurate, but they're all the correct size and brightness. The new moons were tiny, but they posed another Pluto question.
How could something that's only 70% of the size of the Earth's moon end up with three moons?
Astronomers believe that the Pluto system formed when two large objects collided. Studying that collision could teach us about the creation of our own moon. Studying the binary planet system of Pluto and Charon reinforced the theory that our own moon formed through a cataclysmic impact.
We think that the Earth-Moon system formed when a Mars-sized object hit the proto-Earth.
Pluto may be distant, but studying it could help us understand the origin and evolution of our own world.
We think that the process by which satellite systems form around other objects, around planets, will be illuminated by having these new observations.
The new moons and the ongoing discoveries in the Kuiper Belt are evidence that exploration continues to expand our astronomical frontiers.
To think that we're part of history. I mean, it was 27 years ago that James Christie at the Naval Observatory found Charon. You know, then 75 years ago that Pluto itself was founded. And now we're, adding on to that story and, really demonstrating that Pluto is this incredibly interesting place.
Some astronomers have argued that since Pluto is an ice dwarf member of the Kuiper Belt, it should no longer be classified as a planet. Mike Brown, discoverer of Xena, the 10th planet, disagrees.
Let's keep Pluto and let's draw the line underneath Pluto, say anything larger is a planet also. What that means, though, is that we probably will find a few more, and I actually think that's good.
He thinks astronomical history is out here, in the Pluto-Charon system and the Kuiper Belt, waiting to be made.
There are a few more planets, and this generation will find a few more, and maybe the next generation will too. I think that's a very exciting proposition for everybody.
The story of New Horizons may be a tale of high-powered rockets and sophisticated technology, but it's also evidence of human persistence, passion, and boundless imagination.
It's going to be an almost timeless object, that we're building something that will not only outlast the pyramids, but outlast the mountain ranges of the Earth. This will fly through the galaxy essentially unchanged from the way we build it. It will be just that way for billions of years, literally. That's a stunning thing to me every time I think about it.
4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
The New Horizons spacecraft was successfully launched on January the 19th, 2006.
T+40
Fittingly, it carried some of the ashes of Pluto's discoverer, Clyde Tombaugh. Its first crucial mission stage, the Jupiter Slingshot, in February 2007. New Horizons is expected to reach Pluto in 2015.
Humans are explorers. I mean, we're not satisfied just to sit still with the status quo. We want to understand our place in the universe. We want to understand why we're here. Is the Earth unique? Is life unique? And science, and in particular space science, where we're going out to study the planets, is a very important component of that process.
Virtually every place we've sent a spacecraft on a first reconnaissance mission like this, that we find out that our Earth-based notions were flat wrong. So I'll tell you what we expect, but before anything, what we expect is to be surprised.
The possibility of discovering something that nobody's ever seen before is very exciting. It doesn't come along every year, but when it does, that eureka moment is what scientists live for.
Exploring the outer solar system, because it's so far, takes a lot of time. We're talking decades rather than a few years. It requires a lot of patience, a lot of dedication, a lot of perseverance. But it's exciting. It's the frontier. It's the place that we know the least about, and yet the rewards could be huge in terms of what it tells us about the origin and evolution of the solar system. And because it's so far, we just want to know what's there.
And the space theme continues as we show you planes that will be able to launch you into space. How does that work? Follows on Discovery Science.